Hello friends, I welcome you on BYJU'S Exam Prep, India's most comprehensive preparation platform for all the engineers. All the candidates who are joining me live, just quickly confirm your presence in the comment section and tell me whether my audio, visual quality, everything is clear so that we can start with the session. तो दोस्तों स्वागत है आपका बायजूस एग्जाम प्रेप इंडियाज़ मोस्ट कॉम्प्रिहेंसिव प्रिपरेशन प्लेटफॉर्म फॉर ऑल द इंजीनियर्स। दोस्तों आज का सेशन बड़ा ही मज़ेदार सेशन होने वाला है क्योंकि ये हिंदी और इंग्लिश दोनों में होगा, मिक्स होगा। जहाँ पर रिक्वायरमेंट होगी वहाँ हम मोस्ट ऑफ द टाइम इंग्लिश में बात करेंगे और जहाँ पर आपको कुछ दिक्कत होगी उसको मैं अपनी तरफ से खुद भी ट्रांसलेट कर दूंगा और आपको अगर कहीं पर भी कुछ प्रॉब्लम आती है तो आप मुझसे कह भी सकते हैं और मैं उसको हिंदी में एक्सप्लेन करूँगा। तो दोस्तों सबसे पहले डिस्कस कर लेते हैं कि इस सेशन में हम करने क्या वाले हैं और हमारा एम क्या है। इस सेशन में हम क्या अचीव करना चाहते हैं। तो बेसिकली गेट 2023 को हम टारगेट करेंगे। आने वाले the coming GATE 2023 examination we are targeting, and we are going to have a complete revision of power system important formulas. And when it comes to the formulas, you can understand that formulas alone are not going to be enough until and unless the concepts are going to be infused in that. So I will be focusing both in the formulas with regard to the concepts also. तो दोस्तों जल्दी से एक बार लाइक शेयर और सब्सक्राइब कर दीजिए। All the candidates who are joining me live, just quickly like the session, share it with your friends and colleagues so that more and more people are going to be joining with us, and subscribe to BYJU'S Exam Prep if you have not subscribed till now so that you do not miss any of the important session. So please tell me once in the comment section, audio, visual quality, everything is clear so that we can start. Yes, everyone. Shall we start? Some of you may be joining me for the first time, so there is a brief introduction about myself. My name is Ashutosh. As you can see on the screen, I have 11 plus years of teaching experience, completed MTech from ITBHU in 2010, written a couple of books, Engineering Ethics and Power System. My areas of expertise are power system, electrical machines, electromagnetic field theory, material science, engineering ethics, and current affairs. Before we start the session, some of the important inputs I want to give you, because you must have experienced that right now BYJU'S Exam Prep is bringing a lot more stuff for your preparation. So you are going to have on 15th of November, 8 p.m. in the evening, how to ace GATE 2024 with your college or job. So if you are a college going student, if you are doing some parallel job, then if you want to prepare for GATE 2024, then what should be your approach? This session is going to be conducted by everybody's favorite Joshit Singh, having 4+ years of experience. He is an excellent faculty, excellent orator, belongs to civil engineering, but the kind of energy he brings on board is unmatched. So do not miss this session. This is going to be a workshop, 15th November, 8 p.m. Just set the clock. Now, there are going to be some big announcement on the BYJU'S Exam Prep YouTube channels. As you can see, India's best faculty for electrical, electronics, instrumentation, computer science are coming to on one platform, all the faculties on one platform, and this channel in which, जिस चैनल में अभी आप देख रहे हैं सेशन, इसी चैनल में सारे के सारे फैकल्टीज़ इलेक्ट्रिकल, इलेक्ट्रॉनिक्स, इंस्ट्रूमेंटेशन एंड कंप्यूटर साइंस के आपको मिलेंगे, चाहे इंग्लिश हो चाहे हिंदी हो, बियॉन्ड द लैंग्वेज बैरियर सारे सेशंस आपको इलेक्ट्रिकल, इलेक्ट्रॉनिक्स, इंस्ट्रूमेंटेशन, कंप्यूटर साइंस से रिलेटेड इसी चैनल पर मिलने वाले हैं विद ऑल योर फेवरेट फैकल्टीज. One more big announcement, friends. 14th of November, that is Children's Day. So 14th November is going to be your day, and BYJU'S Exam Prep is starting a very impactful series, that is GATE Aimer series. It is going to be a kind of crash course, but I don't want to call it crash course because crash word itself is a negative word. Okay, you understand when the plane crashes. So I understand the meaning of being crashed like that. So I better call it Aimer series. It is Aimer series in which you will be getting the sessions for electrical, electronics, instrumentation and computer science. In this series, what you are going to get? Are you going to get concepts in the form of theory? or you are going to get numericals and practice questions, more practice questions. Actually, you will be getting all of them in this GATE Emerge series. You will be getting the concepts in the form of theory, you will be getting the numericals, practice questions, everything you are going to get under this series. So this series is going to cover almost every topic, every subject of your branch for your upcoming GATE examination. So do not miss this series. It is going to be started on 14th of November. And all the sessions in this series is going to be available in the same channel, this channel. One more important information, my friend, today only, that is 12th of November, 8 p.m. in the evening, you will be having a scholarship test, which is the All India Scholarship Test. And if you attend this scholarship test and you excel well, then you can get up to 90% scholarship on your preparation. So first you have to do is you have to get yourself registered for this scholarship test. Go to the BYJU'S Exam Prep app and follow the instructions and you can register yourself. So now we can start. Let us start with the very basic part of introduction part of the power system, that is power in a single phase circuit. Power in a single phase circuit, you can understand if I am representing the voltage as root 2V sine omega t, and suppose the current in the single phase circuit is root 2I sine omega t minus phi, where phi is the power factor angle. Phi is the power factor angle. Okay. What is V and I? What is V and I? Here, this V and I are RMS values. These are RMS values. Because when you are writing in the sinusoidal form, how you have to write the peak value? The peak value is going to be root 2 times the RMS value. So if you want to find the power and you write the instantaneous power simply as the product of instantaneous voltage and instantaneous current, then you will be getting the final expression like this. This is going to be the final expression, where capital P stands for VI cos phi and Q stands for VI sin phi. Some important conclusions you can make: that the frequency of instantaneous power is going to be 2 times to that of the frequency of the supply. Good morning, Ashok. How are you? Welcome to the session. Okay, so just one important information you can note down here. Let me add one page here. Okay, this is fine. So if you see some important information about the instantaneous power, it has double the frequency to that of the supply frequency. सप्लाई की फ्रीक्वेंसी से 2 times फ्रीक्वेंसी है किसकी? इंस्टेंटेनियस पावर की. Second, if you talk about the average power, if you take the average of this instantaneous power, what will happen? Because any sinusoidal function, if this is a sinusoidal function, and if you take the average for one complete cycle, then this area and this area is going to be cancelled out, and the average of the sinusoidal function is going to be 0. So you can understand that sin 2 omega t term is going to be 0, cos 2 omega t term is going to be 0. So what you will be getting as the average value of the instantaneous power, it is going to be average value of instantaneous power. It is going to be how much? It is going to be simply capital P. What is this capital P? This capital P is nothing but the average power, VI cos phi. Everybody just tell me, are you able to follow this or not? So this is all about the single phase power. Please understand, this is the instantaneous power. This is the instantaneous power. But before I move on, I want to give you some important insights, because these insights are very fundamental for solving the questions in the examination. So I am just going to give some 5 to 7 minutes more on this. Yes. First thing, if you want to write the power, how you are going to write the power? The power is going to be a complex quantity. In general, we are representing the complex power as P plus JQ, where P is the real power and Q is the reactive power. How basically we are defining the real power and reactive power? Power which gives some useful work, that is called as real power, okay, and power which does not give any useful work, that is called as reactive power. Now you must be little bit surprised with the reactive power. See, Ashok, all your doubts, these kind of doubts, what to do with your accuracy in the test series, please ask me these questions either in the end of the session, or you please ask me these questions separately in my personal Telegram channel, that is Electrical by Ashutosh Sir. You can find it on Telegram, because the flow is going to be broken. Please understand this. And these are not just one crisp answer to these kind of questions, because I have to tell you the reality why it is happening. It will take some time. It's not just a one-liner statement I can give you and I can just fool you. I have to invest some time with you. Then only you will understand that how you can improve upon your accuracy in the test series. Okay, so please contact me personally. Now you must be a little bit surprised that real power gives you useful work. Reactive power is not giving you any useful work. So why we are so much worried about the reactive power? Please understand. Electrical power cannot be transferred without reactive power. Why? Almost all the components of power system, require lagging reactive power. Is it clear, everybody? So your transformers are not going to work. No, don't say sorry. It's okay. Your transformers are not going to work. Any magnetic coupling circuit is not going to work. Your loads are not going to work without the reactive power. So you cannot transmit, you cannot transfer the electrical power without reactive power. So reactive power is required. How you are writing this complex power is very important. Suppose you are having a system like this. Suppose this is a generator Okay, this is a bus, and this is going to be some further system. Now suppose this bus is going to have a voltage V angle 0 degree, and suppose this current is going to be I angle minus phi. I am just giving you a simple idea. The current is going to be lagging with the voltage by some angle. Now if I have to write the complex power, how I am writing it? I am writing the complex power as VI complex conjugate. Even if it is going to be a load, whether it is a source or whether it is a load, whenever I am writing the complex power in the polar form, this is called the polar form. Polar form. When any quantity is represented in the polar form, it has two parameters. One is the magnitude. This is the magnitude, and then you have the phase angle. So if the voltage and currents are going to be represented in the polar form, then how you are going to write the complex power? We will write the power as voltage multiplied by the complex conjugate of the current. Some people may be asking this, why we are taking the complex conjugate, and why we are taking the complex conjugate of the current, why not the voltage? So there are two reasons. Number one, the first one is, there are basically two frame of references, absolute frame of reference and we have the relative frame of reference. We have the relative frame of reference. When you are in the relative frame of reference, then there is no problem. You are saying, sir, this is voltage, this is current, and the angle between them is phi. So you can directly make the product of voltage and current phasors and you will get the power. But it's going to be incorrect if you have the absolute frame of reference. Absolute frame of reference means something like this. This is the reference. Now suppose this is your voltage and this is your current. The phase angle with respect to the absolute reference is suppose phi V here, and this is phi I. So you are writing the voltage as voltage magnitude angle phi V, and the current you are writing as magnitude I phase angle phi I. Now if you don't take the complex conjugate and you simply multiply the voltage and current phasors, the phase angle you will be getting is going to be the addition of the voltage and the current phase angles. But when you write the power, you require the relative phase angle between the voltage and current phasor, not the total phase angle. Actually, you are interested in this phase angle. You are interested actually in this phase angle. So this phase angle is going to be the difference of voltage and current phase angles. To get this relative phase angle in the equation, we go for the complex conjugate of the current. Let us try to answer the second question. Why we are taking the complex conjugate of the current, why not the voltage? So the answer is, okay, so let me add one more page here. That is nothing but the sign convention. This is because of the sign convention. This is because of the sign convention. Now, there is a sign convention for the source. If you are writing the complex power for the source as voltage current complex conjugate, and you are writing it as P plus jq, then if P is positive, okay, and Q is also positive, then you are saying P and Q are supplied, because the basic nature of the source is to supply power. So after applying this, if you are getting the positive values for the real and reactive power, it means this much real power and this much reactive power is supplied by the source to the system. Now, any one of that, if you are getting negative, suppose you are getting P negative and or Q as negative, it means what? It is opposite to the convention. What is the convention? That source is going to supply the power. So, if one of these values or both of these values are coming negative, it means P and Q are absorbed. Instead of supplying this much power, actually the source is going to absorb this much real and reactive power. Similarly, you can have the sign convention for the load also. What is the basic nature of load? The basic nature of load is to consume power or absorb power. So, in the same way, if you are writing the complex power as voltage current complex conjugate, that is P plus JQ, if you are getting P positive, if you are getting Q positive, it means P and Q are absorbed. And if you are getting P negative and or Q negative, it means instead of being absorbed, this much real and reactive power is being supplied by the load to the system. So, this is going to be P and Q supplied. I hope it is clear now. So, because of this sign convention we are having for the source and load, we are having the complex conjugate of the current, not the voltage. So, we have completed the discussion for powers in a single phase circuit. Then we have power in a three-phase circuit. The first thing you have to understand what is the meaning of a balanced system. Please understand what is the meaning of a balanced system. If you don't understand this, you may do some mistakes in the examination. Balanced system. If all the information is given for one phase, then all the information can be known for other phases. In the mathematical point of view, you can understand that when you talk about the balanced system, whether you talk about the voltages or the current, the magnitudes are going to be same and they are going to be displaced in time by 120 degree. But this is the physical interpretation. This is the physical interpretation. So, whether it is voltage or current, they are going to have same magnitude and displaced in time by 120 degree. This is how we define the balanced system. Now, if you write the power in a three-phase circuit, please understand how we are writing. Suppose you have three phases A, B, C. For A phase, you are writing the voltage as root 2V sine omega t. So, can you tell me what is going to be the voltage for phase B? If you have all the information for one phase, for a balanced system, very easily you can write all the information for the rest of the two phases. Yes or no? So, if you know the voltage for phase A, what is going to be the voltage for phase B? It is going to be root 2V sine omega t minus 120 degree. What is going to be phase C voltage? It is going to be root 2V, and these are instantaneous voltages because we are dealing with the time. Root 2V sine omega t. Either you can write plus 120 or you can write minus 240. It's your choice. So, these are the voltages. How you are going to write the currents? You can write the currents. Suppose you write the current for A phase. A phase current, suppose you are writing as root 2I sine omega t minus phi. So you have all the information for one phase. Can you write all the information for the rest of the two phases? Yes, because it is a balanced system. So this is going to be IB is root 2I, this is sine, this is omega t minus 120 degree minus phi. What is the current in the C phase? It is root 2I sine, this is omega t plus 120 degree minus phi. So having these voltages and currents per phase, instantaneous values, very easily you can write the power for all the phases. Suppose I am writing the power for A phase. So do you remember the expression for the power in a single phase? Just now we have discussed. It is P1 minus cos 2 omega t minus Q sine 2 omega t. With this formula, you can write the power for B phase also. You can write the power, instantaneous power for C phase also. And just add up all these power, you will be getting the power in a three-phase circuit. This is what I have given you the final expression. The most interesting part of this three-phase instantaneous power is that it is going to be a constant value. There is no time information. There is no information about the time. So it is independent of the time. So we are saying instantaneous three-phase power is constant or independent of the time. It is 3 times the real power, average real power per phase. Is it clear, everybody? Just tell me yes or no. See, we are going in a very systematic manner, and it is going to be a kind of complete revision of this particular subject, power system, for you. So there has to be a minimum strength so that I can get motivation and carry forward the session. So please share it with your friends and colleagues as much as possible. Now let us talk about the three-phase connection. So basically you are having two types of three-phase connections, that is star connection and delta connection. For star connection we have some basic features. You understand, for the star connection, the line current and the phase current are going to be same. So we are writing the line current and phase currents are going to be same. If you talk about the line voltage and the phase voltage, you can write the line voltage is going to be root 3 times the phase voltage. These are the relation. Okay. If you talk about the phasor diagram will take little more time, so I am not going into that. If you want, you can get it from some of my previous lectures. I am just going to give you the final conclusion part. That is, if you talk about the star connection, the line voltage is going to lead the phase voltage by 30 degree. What is the importance of this information? What is the importance of this information? The importance of this information is that if you have the expression or the value for phase voltage, then you can write the line voltage, because you know the magnitude of line voltage. You know the magnitude of line voltage is going to be root 3 times the phase voltage. And you have the phase angle information also, that line voltage for the star connection is going to be leading the respective phase voltage by 30 degree. Are you able to follow this or not? Similarly, for the delta connection, very easily you can write that the line voltage and phase voltage are going to be same, whereas the line current is going to be root 3 times the phase current. And again, the phase angle relation you can write is that the line currents now are going to lag the respective phase currents by 30 degree. In case of star, the line voltages were leading the respective phase voltage by 30 degree, but in case of delta connection, the phase currents are going to be leading the line currents by 30 degree. Is it clear? Is it clear, everybody? Now, one important area from where questions can be expected in your examination is the per unit system. Per unit system we are defining simply as, let me just give you one example. Suppose you have a system like this. Okay. Suppose this is a generator and this is a motor, and you have a parallel line, you have a parallel transmission line. These are the transformers T1, T2, T3, T4. Now you please understand that because of the presence of the transformers in your power system, the voltage level at the generator side is going to be different and the voltage level at the line side is going to be different. Similarly, the voltage level at the motor side is going to be different. So if you want to analyze or you want to make some calculations for this system, it is going to be highly complex. You can imagine how many number of KVL equations you have to write, and all the voltage levels are going to be very, very high. So the calculations are going to be very, very complex. So what we are going to do, we are going to normalize this system. How we are normalizing the system? Normalizing the system means we are going to select a base of quantities, and with respect to that base of quantities, we are going to represent each and every parameter of our system. When I say each and every parameter of our system, then I am interested in the 4 parameters: voltage, current, impedance, and the power. The voltage, current, impedance, and the power at every point, every node in our system, we can write by using that base quantities. So the calculations are going to be simple, and there are a lot more other advantages that we will discuss right now. Out of these 4 quantities, most of the time you will see we are taking the base quantities as voltage and the power, but it is not mandatory. It's up to you. Any 2 of these 4 quantities you can select, and rest of the 2 quantities are automatically going to be fixed because they are interrelated. For example, it's not that always you choose voltage and the power. You can choose voltage and current also. Once you decide the base quantity for voltage and current, automatically the base impedance and base power is going to be fixed. But why most of the time we are dealing with the base quantity for voltage and power is the reason because most of the component in your power system, they are rated in terms of the power rating and the voltage. Is it clear, everybody? At least if you can give me some comments in the comment section, then it will be wonderful. So how we are writing the per unit value of a quantity? We are writing the actual value of the quantity divided by the base value of the quantity in the same unit. As per the usual case, we are having the base power as the MVA base and the base voltage as kilovolt base. Even though I am writing here MVA base and voltage base as kilovolt base, but don't get confused. There are some books in this particular subject which have made this per unit system very complex by multiplying MVA with 10 to the power 6 and kilovolt by 10 to the power 3. No need of it. You remember the simple expression in terms of the parameters. When you put the values, then you take care of the units. So you can write the base current. If you have the 4 quantities I am interested: voltage, current, power and impedance. You have fixed the base for power and voltage. First thing I am going to find is the base current. Base current is going to be MVA, volt ampere divided by volt, that is √3 voltage base, because it is a 3-phase system. Now if you want to write the base impedance I am writing as kilovolt base square upon MVA base. This you have to remember. This can be easily proved by the voltage and the current relation. Then we have another expression for relating the per unit value of the impedance in 2 different base systems, because you must be aware that per unit values are not unique. What is the meaning of this statement? Per unit value is going to be decided by the base you have chosen. If I am choosing a different base, my per unit value is going to be different. If you are choosing a different base, then your per unit value is going to be different, and that is why we see the per unit values are not going to be unique. So we must have a relation to convert the per unit values from one system of base to the other system of base. So this formula you must be knowing this formula, that is Z per unit new is equal to Z per unit old, MVA base new upon MVA base old multiplied by kilovolt base old upon kilovolt base new whole square. Okay. Anywhere if you find any difficulty in any formula, these are very simple formulas that I am discussing right now. So if you have any doubt anywhere, you please raise your doubt. Now let us discuss about the basics of transmission line. So I will be discussing about the conductor types. You see the previous year gate questions, every alternate year there is a possibility that one question you will be getting from this area. So let me just discuss that. If you talk about the transmission line, let me first define transmission line. How we are defining transmission line? It is a group of conductors. Group of conductors transferring bulk amount of power. So your transmission line is not a simple conductor. It's a special type of conductor. Actually, it is a group of conductor which transfers bulk amount of power. We are dealing with 400 kilovolts, 765 kilovolts, 1200 kilovolts maybe. Okay, that is in the testing phase. So these conductors are designed in some of the following ways. The first one is single solid conductor. Then we have stranded conductors, then we have bundled conductors, hollow conductors, and double circuit line is just some modification. So let us discuss about the single solid conductor. Single solid conductor means don't apply much of your brain, just have a circular cylindrical construction for your transmission line conductor, which is the most easy way of designing your transmission line. But there are some serious disadvantages, that is skin effect. What is skin effect? We will discuss in the same session. I will be discussing skin effect, proximity effect, radio interference, corona phenomena, everything, Ferranti effect, all the phenomena we are going to discuss in the same session. So just stay with me. But in nutshell, you can understand what is skin effect. So skin effect simply tells you that there is a tendency in the AC current to get concentrated near the surface of the conductor, and it is the tendency of the AC current, not the DC current. Then why it is called as skin effect? It is called as skin effect because if there is an ideal conductor, then the current is going to be present only on the skin of the conductor. That is why it is called as skin effect. So because of the skin effect, what is happening? The current distribution is going to be non-uniform. Current is going to be only present near the surface of the conductor, whereas if you go to the central core of the conductor, you will find there is no significant current. So if you write the resistance, that is rho L upon A, actually this A is not the physical cross section. This A is the electrical area, electrical cross sectional area. What do you mean by the electrical cross sectional area? Electrical cross sectional area means the cross sectional area in which current is flowing, in which current is present. And because of the skin effect, because of the non-uniform distribution of the current, you can understand this electrical area has been severely reduced. So you can understand the AC resistance, because we are dealing with skin effect in the AC system. That is what I am trying, Ashok. Okay, that is what I am trying. Okay. So, the AC resistance is going to be increased. That is why we are saying AC resistance becomes more than the DC resistance because of the Aiken effect. So, there are more losses. Yes or no? There are more losses, more voltage drop. There are some advantages also if you have a single solid conductor. The advantage is that the mechanical strength is going to be very high. So, what is the impact of mechanical strength? Let me just give you some idea. What is the impact of mechanical strength? Just a moment. Yes. Suppose this is the situation. It may not be visible. Let me use another color. This is called transmission tower, and in some of the European countries and the America or United States, it is also called as pylon. It is also called as pylon. Okay. Suppose this is your transmission tower and this is going to be your transmission line conductor. Then there will be a drop in the shape of the conductor, something like this, and this drop we are defining as sag. And if you see with respect to the ground, this is what we are defining as the ground clearance. Now, if you are saying, sir, mechanical strength is very high, mechanical strength means what? The tensile strength is going to be very high. When the tensile strength is very high, then sag is going to be less. Sag is going to be less. When sag is going to be less, what about the ground clearance? Ground clearance is going to be more. Ground clearance going to be more means less number of towers and height of towers. अगर आपने ग्राउंड क्लियरेंस को ज्यादा कर दिया, ग्राउंड क्लियरेंस आपका है सिग्निफिकेंट है, तो ऑब्वियसली हमें कम नंबर ऑफ ट्रांसमिशन टावर की जरूरत पड़ेगी. यस, और हमारी ट्रांसमिशन टावर की हाइट भी कम होगी क्योंकि ऑलरेडी हमें अच्छा खासा ग्राउंड क्लियरेंस मिल रहा है. Then there is going to be a significant reduction in the cost of the transmission. Then that overall cost is going to be less. So this is the relation. How mechanical strength is going to be important. Is it clear? Now we are going for the second design. The second design is stranded conductor. Now let me just explain this diagram a little bit. What is happening if you have the, let me give you some idea because this diagram is not going to be sufficient. Little bit of skin effect I have to tell you. What is happening? Suppose if this is your conductor, okay, and suppose this is the cross section area in which current is going to be concentrated or current is present. So this distance from the surface of the conductor till you get effective current, till you get effective current, this distance we are calling as skin depth. And your skin effect is inversely proportional to skin depth. If this skin depth is going to be less, it means more non-uniformity in the current. It means more serious skin effect. So there is an inverse relation. Lesser and lesser skin depth, more and more is skin effect. Now what I am going to do, in order to have a reduced skin effect, suppose you have two cases. This is one case. This is one conductor A. And suppose now I have reduced the cross section of the other conductor. I am reducing the cross section of, Ashok, please wait. I am having another conductor. One conductor I am having A with some skin depth. Suppose this is the skin depth. This is the skin depth, representing it with del. I am having another conductor having the reduced cross section, but I am not changing the skin depth. So skin depth is going to remain as same. So the skin depth is same, but the cross section has reduced. If you compare these two conductors, conductor A and conductor B, very easily you can understand that skin effect is going to be more in A conductor in comparison to skin effect in B conductor. Because the non-uniformity in current is going to be more in A conductor rather than in the B conductor. Are you able to follow this? Just tell me yes or no in the comment section. Tell me yes or no. If you reduce the cross section, then for a given skin depth, the non-uniformity is going to be less. It means instead of having a single solid conductor of a large cross section, if we have a smaller cross section like this, if we have a smaller strands, these are called as strands, instead of a single solid conductor, then what is going to happen? Then what is going to happen? Just see here. Number one, skin effect is reduced, but please remember it is not removed. You have reduced the skin effect, that is accepted, but the skin effect is still present because it is not 100% removed. Second, mechanical strength has reduced. Mechanical strength has reduced. गए थे हर भजन को ओटन लगे कपास. So we were actually targeting to reduce the skin effect, but the time we started reducing the skin effect, we have got two more problems, and these are bigger problems. Number one, the mechanical strength has reduced, so we have to do something for it. At the same time, because of the sharp corners in the conductor, these are the sharp corners or the not smooth surface. At these sharp corners, the electric field stress is going to be very high, so that the possibility of corona will become very high. The possibility of corona will become very high. So corona is going to become high. So we have got two problems, mechanical strength and the corona. Everybody just tell me, are you able to follow this? Yes. How to deal with the mechanical strength? So what we are doing, just see here. What we are doing here. Just see here. Sir, you are saying a skin effect is still present. You are saying, sir, skin effect is still present. So what I am going to do is, sir, I will remove this core strand. These are all aluminum strands. Okay. And I will remove this core strand and I will replace it with a steel strand. Why, sir? Because of the skin effect, still no significant current is flowing in the core strand. So if no current is flowing, why not replace it with a material which is having more mechanical strength, so that overall mechanical strength of the conductor can be increased? Yes, such a conductor we are defining as ACSR conductors, that is steel reinforced aluminium conductor. Aluminium conductor. Is it clear? Now, if all the strands are going to be of aluminium, okay, all are aluminium. This is also aluminium. This is also aluminium. This is also aluminium. This is what we are calling as homogeneous stranded conductor. And if all the strands are going to be of aluminium, we are calling it as all aluminium conductor. AAC, all aluminium conductor. Is it clear? So, and this ACSR is called as composite stranded conductor. Composite stranded conductor. So we have solved one problem, that is of mechanical strength. Mechanical strength we have improved by introducing a steel strand in the core. But it's not that only one strand is going to be of steel. There may be more than one strands also. Okay. So for the ACSR conductor, especially for the ACSR conductor, we are saying, we are representing the ACSR conductor by X oblique Y. This is how we represent the ACSR conductor, where X and Y are numbers. Numbers of what? If X is greater than Y, then X is going to be the number of aluminium strand and Y is going to be steel strands, number of steel strands. If Y is going to be more than X, then X is going to be the steel strand and Y is going to be the number of aluminium strands. Why? Because obviously the main function of a conductor is to transfer power, to carry current. So always the number of aluminium strands has to be more, and the number of steel strands are just there to give you the mechanical strength in the conductor. So this is how we represent the ACSR conductor, X oblique Y or Y oblique X. It depends whether X is greater than Y or Y is greater than X. So the larger number belongs to the number of aluminium strands and the smaller number belongs to the number of steel strands. But if you talk about the pattern of a strand, whether it is ACSR conductor or any stranded conductor, then the pattern of strands is going to be 1, 6, 12, 18, 24, 30, 36, etc. So it is going to be a multiple of 6, as you can observe here. This is the first layer. This is what we are defining as the first layer. So first layer is going to have only one strand. If you go for the next layer, that is the second layer, this is what we are defining as the second layer. This is the second layer. So the second layer is going to have 6 strands. 1, 2, 3, 4, 5, 6. If you want to add one more layer, that is the third layer, then it will be 12 strands. So this is going to be the pattern of strands, whether it is a homogeneous standard conductor or whether it is going to be a composite standard conductor. Is it clear, everybody? Just tell me yes or no in the comment section. Are you able to follow this? Now let us write the diameter of the standard conductor. How we are writing the diameter of the standard conductor? Please see here. It is going to be 2n minus 1 d, where n is the number of layer and d is the diameter of each strand. I have given one example. Suppose n is equal to 2. It means what? This is the first layer. This is the second layer having 6 strands. Okay. Now if you observe, what is going to be the diameter of this conductor? This is d, this is d, this is d. So total diameter is 3d. If you put it in the formula, what is n? N is the number of layer, 1 and 2. So n is 2, so it is going to be 2 into 2 minus 1, that is d. So it is 3d. This is going to be the total diameter of the standard conductor. Similarly, you can write the total number of strands. Total number of strands is going to be given by this formula, that is 3n square minus 3n plus 1. But please remember, this formula is applicable only when you are starting n is equal to 1, that is the first layer. And first layer is the core strand. So for example, if you again take the same example, this is your core strand, first layer, then second layer having 6 strands. How many total strands are there? 7. So if you put it in the formula, what is the number of layers? Number of layers is 2. So it is going to be 3 into 2 square is 4 minus 3 into 2 plus 1. It is 12. This is 6 plus 1 comes out as 7. I hope it is clear. Everybody, are you able to follow this? If you don't comment, then how I'm going to know that you are able to follow this or not? At least you can comment, or you can take the help of your younger brother and sisters. Then we have bundled conductors. Why we are going for bundled conductors? Because one problem we have solved. The problem is how to maintain or increase the mechanical strength of the standard conductor. So we have used the ACSR conductor to increase the mechanical strength. Mechanical strength we have solved. What about the corona? Corona we are going to solve by using, yes Ramakrishna, by using the bundled conductors. The moment I say bundled conductors, what is the first thing which comes in your mind? Yes, everybody. What is the first thing comes to your mind? Let me give you some idea. What is the first thing comes to your mind? So what is happening here, friends? Let us understand. When I say bundled conductors, let me use another color. When I say bundled conductor, then what is the first thing that comes to your mind? The basic idea is, if we are having a conductor like this, I am going to break this conductor into smaller subconductors and I am going to give some spacing. Instead of having a one single conductor, I am going to break into smaller subconductors and I am going to give them some spacing. So what will happen if you are having a situation like this? Suppose you have broken this conductor into two parts and these are going to be subconductors. These are subconductors. So what you are going to do here is, you are going to increase the GMR, geometric mean radius. We'll discuss what is geometric mean radius, don't worry. Even if you are comfortable or not, I am going to give you some insight into the GMR, GMD and GMR, the concept of GMD and GMR. So basically by using the bundled conductors, GMR is going to be increased. So if GMR is increased, then number 1, electric field stress at the surface of the conductor is given as V phase upon GMR ln GMD upon GMR. Now this is going to be logarithmic. So if you are increasing the GMR, electric field stress is going to be reduced, and obviously corona is going to be reduced. There are some other conclusions in the bundled conductor. What about the inductance per phase? It is 0.2 ln GMD upon GMR. This is millihenry per kilometer. You are saying, sir, GMR increased, so inductance per phase reduced. What about capacitance per phase? It is 2 pi epsilon naught ln GMD upon R. Please note down, when we are writing the capacitance formula, we are not using the word GMR. Why? Because the GMR is defined for the internal flux linkage. But when you have the capacitance calculation, you are dealing with the electric field. Electric field, no flux is going to be present inside the conductor. Electric flux cannot be present inside the conductor. So using the concept of GMR in case of capacitance calculation is not correct, and that is the reason we are simply writing R. But this R is GMR without 0.7788 factor. Without this factor, the whole calculation is same as if you are doing for GMR, it is going to be same for R. So you are saying, sir, GMR is increased, this is increased means denominator is reduced, so capacitance is increased. Sir, what about the surge impedance? Surge impedance is defined as under root L by C. Sir, L you have reduced, C you have increased, so the surge impedance is reduced. Sir, what about the surge impedance loading? Surge impedance loading is V rated square divided by ZC. ZC you are saying reduced. For a given rated voltage, the surge impedance loading is increased. Sir, what about the stability? Now understand. Sir, you are saying P is equal to mod V1 mod V2 upon X, and this is sin del. Now, sir, you are saying P max is mod V1 mod V2 upon X. X is omega L. L you are saying reduced, so X is reduced. X reduced, keeping V1 V2 same, P max is increased. P max increased means what? P is equal to P max sin del. Sir, P max increased. For a given constant power being supplied, sin del has to be reduced, or del has to be reduced. Del reduced means what, sir? This is P, this is del, this is your sinusoidal variation of the real power. Now, this is the del is equal to 90 P max situation. Suppose you are here initially, and because of using the bundled conductors, now you have reduced the operating del value and you have come here. So definitely the stability margin has increased. As much you are away from del is equal to 90, that is the border. Beyond this, it is unstable. 0 to 90, it is stable. So more is the stability margin, more is going to be the stable. So stability is also going to be increased. So these are some of the important conclusions about the bundled conductor. Is it clear? Now, if you talk about the bundled conductors, suppose this single solid conductor is divided into n number of subconductors. All the subconductors will be acting like if they are connected in parallel, because the voltage is going to be same everywhere. See, voltage is same everywhere, all the strands. Current is going to be different, and total current is going to be the sum of I1, I2, I3 up to In. So if you relate the radius of the subconductors, that is as Rb for bundled conductors, if this is R, it is going to be R upon under root N. Either you can remember this formula, or you can do one interesting thing that I will tell you, so that you can apply it anywhere. See what is happening here. You are saying, sir, this single solid conductor we are going to divide into n number of subconductors. This is 1, this is 2, and this is n. So this is going to be I1, this is going to be I2, and this is going to be In, and this is going to be total current I. Voltage is going to be same. Yes. So you can write the Kirchhoff's current law, KCL. It is going to be I1 plus I2 plus In. But current you can write as current density multiplied by the cross-sectional area. Current density is going to be constant for transmission line, because transmission line load tappings are not allowed. You cannot connect the load to the transmission line in general, especially the primary transmission. You cannot connect the load because the voltage is such a high level. So when load tappings are not allowed, the current density is going to remain as constant. If the current density remains as constant, then you can understand current is directly proportional to area, or you can say current density is going to be constant both the sides. So this current expression, can I write in terms of the area? Yes. Can I write A is equal to A1 plus A2 plus AN? Yes or no? I am going to give you a shortcut in the examination which you can directly use. But area, circular area is defined as pi r square. Pi is going to be same both the sides. So can I equate it in terms of the square of the radius? Can I write it like this? R square is R1 square, R2 square, Rn square. Can I write like this? Yes or no? Yes. If R1, R2, Rn, they all are equal, then you can write this formula as Rb. So it is going to be R square is equal to N times, this is Rb square. So you can write Rb is R upon under root N. Is it clear, everybody? Are you able to follow this for the bundled conductors? Now let us talk about the capacitance calculation. Capacitance calculation, we are having the single phase 2-wire system, as you can see here. For capacitance calculation, we cannot go without the neutral point, because voltage cannot be expressed without a reference. You cannot say that you are the most powerful person in the world till you have a reference. Okay? Because some other is going to come who is going to be more strong than you. So always when you talk about potential, you always talk with respect to a reference. There is nothing called absolute voltage. Voltage is always expressed in terms of the voltage difference, potential difference. So you are writing the capacitance from, for A, excuse me, capacitance of A conductor with respect to the neutral point, and capacitance of B conductor with respect to the neutral point, with the formula. Okay. Sorry, it is not calculation of capacitance, it is calculation of inductance, sorry. So next topic we will be discussing about the calculation of capacitance. First, let us talk about calculation of inductance. I thought it is capacitance. So, for single phase 2 wire system, what is happening? It is the situation something like this. Suppose this is your generator, this is the forward one, this is the load, and this is the return conductor. This is the forward conductor, this is the return conductor. This is A, this is B. The situation is something like this. So, if you write the inductance, you are going to write it like this. For A conductor, I have written it. Let me just write it again so that you can read it properly. It is going to be mu naught mu r. When you are writing for the internal flux, you are inside the conductor. So, this is material divided by 8 pi plus mu naught mu r. Now, when you are outside the conductor, you are dealing with the medium. So, this is medium divided by 2 pi. Now, actually this is ln d by r, but I am expressing it like ln 1 by r minus, or first let me write like this, it is ln d by r. This is what you are getting as the expression for a conductor inductance. Is it clear, everybody? And this is Henry per meter. This is Henry per meter. This is what you have got for the internal flux, inductance due to the internal flux, and this part you are getting for inductance because of the mutual flux. Okay. Now, this second expression I have actually expanded more because I want to explain little more terms related to the inductance part. So, I have written mu naught mu r medium upon 2 pi ln 1 upon r as it is, and minus mu naught mu r medium upon 2 pi ln 1 upon d. If you remove this minus, you make it plus, it will become mu naught mu r medium upon, this should be 2 pi ln d. Yes or no? Minus 1, if you make plus 1, then automatically it will become d by r. So, just way of representing it, how I have expanded it, just let me write it here. Yes. So, the final expression in the expanded form, I will tell you the expanded form also, and I will tell you the compact form also. So, you are having LA as mu naught mu r conductor divided by 8 pi plus mu naught mu r medium upon 2 pi, and this is ln 1 upon r minus mu naught mu r medium upon 2 pi ln 1 upon d. So, how we are defining it? This is going to be L self due to internal flux. Okay, self inductance because of the internal flux. This term belong to again L self due to external flux or mutual flux. The last term is L mutual. It represents the mutual inductance. Whenever you want to write the expression for the mutual inductance, always use this expression mu naught mu r medium upon 2 pi ln 1 upon d. Forget about the negative sign. This is the standard way of writing the mutual inductance due to external flux. Now let me use little bit of Hindi also. कुछ चीजें हमारी जिंदगी में अपने आप अच्छी हो जाती हैं, हम कुछ करते नहीं हैं और वहां पर हमें पता चलता है कि इस दुनिया में भगवान भी है. तो एक पावर सिस्टम इंजीनियर की दुनिया में भगवान कैसे आए, देखो हुआ क्या. With lot of effort, बड़ी मुश्किल से उसने इंडक्टेंस का फॉर्मूला निकाला उस पावर सिस्टम इंजीनियर ने, और उसको लगा कि इसको याद करते करते तो पूरी जिंदगी निकल जाएगी. Because it's going to be very complex formula. It's not one formula you have to remember. You have to remember hundreds and thousands of formulas. So God has given you something to relax. God is saying, listen, medium is air. Yes or no? Overhead transmission line. What is the medium? The medium is air. And for air, what is mu r medium? It is 1. And because of God's grace, conductor material we are choosing as aluminium. And if you see the mu r for aluminium, it is very close to 1. This is because of God's grace. You have not done anything. If you put these values in this expression, what will happen? Just see, I am writing here. LA is going to be mu naught upon 8 pi plus mu naught upon 2 pi ln d by r. Yes or no? Now I am going to take mu naught upon 2 pi as common. So if you write mu naught upon 2 pi, it will be 1 by 4 plus ln d by r. This 1 by 4 I am going to write as ln e raised to the power 1 by 4. With some mathematics, I hope you can understand this. Plus ln d by r. This is going to be mu naught upon 2 pi ln d e raised to the power 1 by 4 upon r. Further, I can write mu naught upon 2 pi ln d upon r e raised to the power minus 1 by 4. And this e raised to the power minus 1 by 4, e raised to the power minus 1 by 4 is nothing but 0.7788. And this r into e raised to the power minus 1 by 4 we are defining as r dash. This is nothing but geometric mean radius. I hope it is clear. And this d represents GMD. So how you are writing the expression for inductance as, what is mu naught? Mu naught is 4 pi 10 to the power minus 7. This is 2 pi. This is ln GMD upon GMR. And my friend, this is Henry per meter. The unit is Henry per meter. Now 2 pi is going to be cancelled, and I will write it 2 into 10 to the power minus 1. 10 to the power minus 6 I have taken from here, and I will make this Henry as millihenry and this meter as kilometer. So it will become ln GMD upon GMR, and the unit will become millihenry per kilometer. Or this you can write as finally the final expression now. Now the final expression. The final expression becomes LA as 0.2 ln GMD upon GMR, and the unit becomes millihenry per kilometer. This is the final expression. If you are dealing with three phase, then simply you can write inductance per phase by using this formula. It is GMD system, GMR system, millihenry per kilometer. I hope you remember that. But this is for a three phase. This is for a three phase. But if you are having a single phase, my friend, again I am writing, let me use one more page here. If it is a single phase two wire, if it is a single phase two wire, if it is a single phase two wire system, then my friend LA is going to be 0.2 ln GMDA upon GMRA millihenry per kilometer. LB is going to be 0.2 ln GMDB upon GMRB millihenry per kilometer, and total inductance or loop inductance is going to be LA plus LB. If it is a single phase two wire system, then this is the way how you have to write it. If it is a three phase system, then directly you can write it. Is it clear, everybody? So after this conductor type, I will stop. Okay. Then we will meet in some other session, because I don't find you quite excited about the session. So in the next session we are going to continue, but let me complete this. Now let us talk about the capacitance calculation. As I told you, you should not read even a single second, because you are already on cloud. Okay. Anyways, just leave it. So capacitance calculation for a single phase two wire system, as I told you, capacitance calculation you cannot do without the reference, that is the neutral point. So this is going to be your neutral point. This is going to be your neutral point, which is equidistant. dA, dB are going to be at equal distance. You have the charge densities plus Q and minus Q, radius R1 and R2. How you are writing the capacitances? Capacitance of conductor A with respect to the neutral point is going to be 2 pi epsilon naught epsilon R ln D upon R1. This is farad per meter. Similarly, this should be R. Okay. And this should be epsilon R. Similarly, you can write for the B conductor with respect to the neutral point as 2 pi epsilon naught epsilon R divided by ln D upon R2. This is also farad per meter. If R1, R2 same, then CN and CBN are going to be same as it is written here. And if you want to write the line capacitance, the capacitance between A and B, then definitely it is going to be a series combination of two equal capacitances, CAB and CBN. So CAB is going to be 1 by 2 times CAN, or you can write it as 1 by 2 times CBN. Is it clear, everybody? Yes? So what is going to be the expression for the line capacitance? Already it is mentioned here. It is going to be pi epsilon naught epsilon r upon ln d upon r if r1 and r2 are same farad per meter. Directly you can write. Effect of earth in the capacitance calculation. You must be aware that when it comes to the capacitance calculation, there is a possibility of induced charge because earth is going to be acting like a conductor at zero potential. So, when a conductor, charged conductor is near or very near to the surface of the earth, there is a possibility of induced charge. That induced charge we are going to take up in the form of image charge, Kelvin's image law, you must be aware with that. So, for a single phase 2-wire system, what we are doing, A and B are the two conductors, we are taking the image of A is A dash, this is plus Q, this is minus Q, equidistance from the earth's surface, this is H, this is H. Similarly, we are having the image of B conductor also, B image is B dash, this is minus Q, this is plus Q, equidistance from the surface of the earth. So, when we are writing the capacitance for A conductor with respect to the neutral point, it is going to be, just writing it again so that it is visible, 2 pi epsilon naught epsilon r ln g by r. This is the normal term we were getting earlier also, but there is one more term, that is 1 upon, and this is under root 1 plus d upon 2h whole square. This is h, 2h whole square, and this is farad per meter. But if 2h is very high, sorry, yes, 2h is going to be very high in comparison to d, then this ratio d upon 2h is going to be negligible. So, this whole ratio 1 upon under root 1 plus d upon 2h whole square is going to be equal to 1. So, it is simply going to come as the earlier expression, that is 2 pi epsilon naught epsilon r ln d by r farad per meter. This is when the effect of earth is neglected. Effect of earth is going to be neglected if the height of the conductor is sufficient, is neglected. Is it clear, everybody? This is what I was telling you. If d upon 2h is going to be very small in comparison to 1, then we can say that effect of earth can be neglected and you will be getting the expression as earlier. Let me talk about the charging current. You can get a question on charging current, how we are defining charging current. Please understand this. The most simple expression of equivalent circuit is going to be something like this. For your transmission line, so this is going to be, let me just use a different color. This is going to be R, L, C, and this is going to be G. R represents the I square R losses. L represents the magnetic energy stored. C represents the electric field energy is stored. And what this G represents, this is important. It represents the leakage current through insulator. So for your notes, something important. This G value or the leakage current through the insulator, it depends on two things. Number one, atmospheric condition. Atmospheric condition is going to be deciding the amount of leakage current. If it is a wet condition, if it is a storm, then definitely leakage current is going to be more. And second, the surface condition of the insulator. Surface condition of insulator. I hope it is clear for everyone. Now see what is happening. This is going to be the sending end voltage for your transmission line. This is the sending end current. This is the receiving end voltage and this is the receiving end current. The current which is bypassed because of the presence of this capacitance is the charging current. This current IC we are defining as the charging current, and how we are defining it? It is the current which is sent by the sending end but does not reach to the receiving end because of the presence of shunt capacitance. Charging current सेंडिंग एंड से भेजी हुई वो करंट है जो रिसीविंग एंड तक नहीं पहुंचती है, बीच में कहीं खो जाती है बिकॉज ऑफ द कैपेसिटिव एलिमेंट. तो इसको हम डिफाइन कैसे कर रहे हैं? चार्जिंग करंट हमेशा हम पर फेज निकालेंगे. पहली इंपॉर्टेंट बात, चार्जिंग करंट विल ऑलवेज बी डिफाइंड इन टर्म्स ऑफ पर फेज. So charging current is phase voltage divided by per phase capacitive reactance. Capacitive reactance is 1 upon 2 pi Fc, so it becomes upside, and this is the charging current. Now, okay, so basically this capacitance per phase, he has written as capacitance per phase per kilometer multiplied by the length of the transmission line. This is what is written here. I hope you understand that. So if you see, this capacitance per phase per kilometer is going to be a constant, because once you design your transmission line RLC, it becomes constant. You are not changing the GMD, you are not changing the GMR, you are not changing the conductor material. So RLC becomes constant, and that is why they are called as the transmission line constant. G is a variable because G depends upon the atmosphere condition and the surface condition of the insulator. So we are not calling G as a constant, but RLC is a constant. So 2 pi F is a constant, supply frequency is constant, C is constant, or suppose F is variable. So you can write the charging current as directly proportional to VFL. Is it clear, everybody? So we are writing charging current as, let me use another page, or simply we can write it here also. Charging current is directly proportional to VFL. V is the operating voltage, F is the operating frequency, supply frequency, and L is the length of the transmission line. So very easily you can understand, for long transmission line, the length is going to be more, so charging current is going to be more. Ramakrishna is asking, sir, where this charging current is going to be flowing? See, this charging current is not, you say, actually flowing. This circuit is actually a model. Your transmission line does not look like this. It's simply a model to represent various phenomena in your transmission line. Why we are representing R here, L here, C here, G here? To represent various phenomena. So because of the capacitive element in the line, because of the capacitive element in the line with respect to the ground, actually it is acting as a stray capacitance with respect to ground. Are you getting that? So we are simply modeling it. We are representing the phenomena. So don't get into that you want to see this current to be flowing. It's not flowing. Current is only flowing in the conductor like this. Are you able to follow this? Yes? It's about constant conversion of magnetic field energy and the electric field energy. Are you getting that? Magnetic field energy, electric field energy. It's like an electromagnetic wave. So you have to go up to that level to actually get into that. So don't get confused with that. It's not flowing anywhere. It's simple the model, simulation, representation. Okay. So anyways, we were defining charging current. I will tell you one interesting way of finding the charging current. For any transmission line. For any transmission line, very easily you can find the charging current. By using the ABCD parameters, irrespective of the type of the transmission line, you can represent your transmission line with the ABCD parameters. Yes or no? Sending end voltage, current, receiving end voltage, current. So you can write Vs is AVR plus BIR and Is is CVR plus DIR. Now you are saying, sir, I want to know what is the charging current. So please understand from the previous question. If I put it on no load, so IR is going to become as 0 or open circuit. So if the receiving end is at no load, it is open circuited. So whatever current is coming from the sending end, that current is just going to the charging current. So we can say no load condition, IR becomes 0. So you can write the supply current will be equal to the charging current, that is C times VR, and please understand it is the phase voltage. We always write the ABCD parameter equations in terms of the phase values. Okay, always write in terms of the phase values. So don't get confused. So this is going to be your charging current. And what is this VR phase? This is the no load receiving end voltage. No load receiving end voltage. Is it clear, everybody? Now let us talk about the double circuit line. Double circuit line is nothing but using the two parallel circuits for the same phase. Two parallel circuits for the same phase like this. So you can understand what will happen. The effective reactance is going to be reduced. So more power you can transfer. Yes or no? Because you are writing the power transferred is mod V1 mod V2 upon X, and this is sin del. So if X you are reducing, definitely you can increase the power which can be transferred from the source to the load. The main question comes for the double circuit line is, because GMR you can easily calculate. GMR you can easily calculate. GMD, GMR you are comfortable, or should I tell you something? GMD, GMR should I tell you, or you are comfortable? So you can understand that GMR very easily you can write. Yes or no? Because double circuit line means for A phase you are having A1 and A2. Can you write the GMR? Yes, very easily you can write the GMR. Writing the GMD is going to be very difficult for the double circuit line. So for the double circuit line, I am just telling you one way of writing the I am just writing the GMD. So I am writing the GMD as GMD A, GMD B, GMD C, 3 GMD. How many GMD you want? 1. So it is 1 by 3. Are you getting this? This is what we have to write when we have to find the GMD. So this GMD A, GMD B, GMD C we are replacing as DAB equivalent, DBC equivalent, DCA equivalent. Instead of going to GMD, because it is going to be very complex in case of double circuit line, we are going for DAB equivalent, DBC equivalent, DCA equivalent, which is nothing but the GMD only. How we are writing DAB equivalent? Listen here. Each and every distance between A1, B1, distance between A1, B2, distance between A2, B1, distance between A2, B2. How many distances? 1, 2, 3, 4. How many distance you want? DAB. DAB is just a distance. So power is 1 by 4. Can you write DBC equivalent? Yes. It is going to be DB1C1, DB1C2, DB2C1, DB2C2 power 1 by 4. Can you write DCA equivalent? Yes, it is going to be DC1A1, DC1A2, DC2A1, DC2A2 power is 1 by 4. So if you have a double circuit line, just try to write these expressions, you will be getting the GMD. Okay. So let us stop here. Okay. Let us meet in some other session and let us try to figure out some more. That is the remaining part. Is it clear, everybody? Till now what we have discussed, if you have any doubt, you can ask me. Yes, everyone. So you will be getting the complete PDF. You will be getting the complete PDF in this Telegram channel, that is Electrical by Ashutosh Sir. This is my personal Telegram channel on BYJU'S Exam Prep. Yes, I will come to your doubt, Ashok. Please wait. See, as such, the next session is not yet planned because we are coming up with another new series. Okay. So definitely there also power system is going to be discussed, because there is a lot more to be discussed, but there has to be a minimum strength from your side so that we can continue with such a large session. Approximately we are going to close around 2 hours. So that is the reason. Otherwise I was planning to give some more concepts here, but let it be in some other session. Ashok, you please ask your doubts separately to me. This is my personal Telegram channel. Okay, you can just drop a message and we will connect. Okay, Ramakrishna. If you want any other assistance, yes, obviously protection is very important. Circuit breaker and relays, these are 2 important areas from which questions can be asked. Okay. Is it clear? See, if you want, then I can plan a session, no problem. If you want, I can plan one more session for power system. Okay. But it depends on you. If you want it, I will get it. I will get it done. But you have to tell me. So all the candidates who are watching this session live, if you want the second part of this session, please tell me in the comment section of this video, or you can drop a message separately in this personal Telegram channel. This is my personal Telegram channel on BYJU'S Exam Prep. Okay, so I will be planning that session and we'll be discussing the other important areas also. So thank you so much, friends. Take care of yourself, and it was a great time talking to you. I hope you got some concepts and formulas for your subject power system, and let us meet in some other session to discuss the remaining part. Thank you so much. Take care. Thank you.